Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Here we're going to discuss on phasor relationship for circuit element. As we have discussed in the class, I have stated that in phasor we can also represent the relationship in our circuit elements such as resistor, capacitor and inductor. So for the first one, resistor element. If you look at your slide here, phasor relationship involved with resistor, and over here we know that a passive element, current entering this passive element will have a positive input, and current leaving this passive element will have a negative output. Okay. And then if you want to relate this with phasor, we know that in time domain we have a current. If we write it down in time domain, current is equal to some magnitude with some cosine omega t plus theta, and this theta is the theta I, current theta, and this is in time domain. And as we know, we want to enter from time domain from DC. Time domain is a DC form. We're about to enter the AC form. This is a time domain, and this one is a frequency domain. And if you want to relate this with resistor, current, this is a resistor, this is a current, and some voltage drop across this resistor, and we can say that voltage, this is Ohm's law, voltage is equal to current into resistor. So if we want to write this down in terms of time domain, this is how we write it. And based on this part, this is a time domain. If we want to convert it to phasor form, we know that there are three types of phasor form, right? So the first is a polar form. Second is the exponential form. Exponential form is Im exponential of j some omega t plus theta I. And we also have another form, which is the rectangular form. The real part plus the imaginary part. So if we want to, maybe this one first. If we want to convert this into exponential form, this one is equal to Bm e j omega t plus theta v. Yeah, this one actually coming from this Vm e j omega t plus theta v, and also this equal to the current, which is equal to Im cosine Im e j omega t plus theta I, and into R. Okay, so I just did it first. All right, then we know that this is in time domain. Time domain. Time domain. And if you want to enter a frequency domain, then we can divide this equation by E j omega t, so that we eliminate the t here, right? So if we divide that, we will get Vm E j j theta v, and equal to Im E j theta I into R. Okay. And we know that the phasor form for voltage is equal to Vm E j theta V, right? So we can actually substitute this into the equation we have created now. So if we substitute that, we will have V, which is equal to current into R. And if we write this in terms of impedance form, voltage is actually equal to impedance R of I. And over here, we can rearrange the equation, and we will have a current, voltage divided by current, which is equal to R plus J0. We usually will usually not write anything here, so we will get only R there. So how to represent this in terms of complex plane? Okay, and from here we actually have a Vm theta V divided by Im theta I, which is equal to R and 0 degree. 0 degree. How do I know this? This one is actually coming from this. We know that the real axis, this is a real axis, this is imaginary axis. The real have no degree there, so it takes 0 degree here. Okay, so based on this part, we know that the theta v minus theta I is equal to 0 degree, or we can say that theta v is equal to theta I, and this means that there's no phase difference, so they are in phase. Okay, in phase. So how do we draw this? Maybe this is for the current. For the current here, and maybe for the other one is voltage here. Okay, so they are in phase. In terms of complex plane, there is no phase difference, so they are in phase. Okay, all right. We will continue later. Thank you.